Now, why are these called digital signatures? Because these digital signatures can be used to verify the authenticity of the server. So since it is digitally signed by Google Certificate Authority, that is the private key of the Google would have been used to sign this particular public key. So this digitally signed public key would be decrypted and the authenticity of the server, that is gmail.com in this case, would be established. Hi everyone, this is Srish and today we're going to learn about security on the internet. What is encryption? What is decryption? What are the different types and how do they work? How the security of your data on the internet is ensured? What is SSL? What is TLS? How does HTTPS work? What are the most important types of security attacks that happen on the internet and how are they prevented using these techniques? We'll start from the basics, but we'll cover everything in detail. So let's get started. So what is encryption? Primarily during encryption, we translate the data from a readable format into a non-readable format so that it cannot be accessed by any unauthorized person. So let's understand with an example. Let's say you are a client and there's a server and they both are sitting at two different geographical locations and they are connected through internet. And there's a person P who's trying to read through all the bytes that is flowing between these two servers. Now what happens is, if let's say you're a client and you're filling in a form and sending all your personal data on that server, this particular person would be able to read through all the messages and the data would be compromised. Similarly, if your server is trying to send some data back to you, let's say there's a bank server and it is trying to send some data back to the client, let's say it's trying to send the bank balance, this particular person will be able to read the data if the data is not encrypted. Right. So when we talk about the security on internet, we primarily deal with three things. CIA. C stands for confidentiality, I stands for integrity, and A stands for authenticity. When we talk about confidentiality, right? So as discussed, the data that is originating from my system or the data that is originating from the server should be only readable by the person who's has been authorized to read it. It should not be read by any other person. And let's say even if it is read by any other person, they should not be able to decrypt it and make any sense or use that data in any form. It should not be a usable form of data. Now let's say what is integrity. Integrity is any data that I'm sending should not be tampered in between. So let's say if my bank server is telling me that you have an X amount of bank balance, it should not be tampered and somebody in the middle tampering my data and changing the X value to the Y value. So that should not happen. The internet should ensure that the data has not been tampered with. That is integrity. And when we talk about authenticity, so no server should act as a proxy server, as in your bank servers should be the actual servers that you should be talking about. The internet should ensure that your packets are routed, the data is routed to the correct server and it is coming back to the correct client as well. Now when we talk about the type of encryption, so basically encryptions and decryptions on internet ensures all these 3 points are taken care of. When we talk about types of encryption, we have symmetric type of encryption, we have asymmetric type of encryption, and then there is a third type that is a hybrid type. That is nothing new but a combination of symmetric type and asymmetric type, and that is used in the TLS that we are going to discuss about. So let's talk about how symmetric encryption works. So one of the primary requirement of symmetric encryption is the client and the server should use the same key. Now, when you're using the same key, right, and when you're using the same algorithm as well, so any message that originates from the client should be encrypted with the same key and the same algorithm, and the same algorithm and the key should be used to decrypt the message. Now, let's say if you have a message, right, and I've encrypted it with K1 key. Now my encrypted message as well as the algorithm goes on the network, and the server now basically knows the algorithm that I've used, the encrypted message it has, and it will use the same key that it possesses to decrypt the message, and it reads the message, and similarly vice versa happens. Now let's understand this with an example. So let's say clients wants to send the server a simple message, hello. Now let's say they both accept an algorithm that will shift the letters by X characters. Okay, what do I mean by that? So let's say if the value of X is 1, your character jumps by 1 character. So X becomes Y, A becomes B, and B becomes C, and so on and so forth. So let's say if you have hello, HELLO. So let's say if your value of X is 1, and here 1 becomes my key. So the algorithm is known to both client and server that I'm using, let's say X hopping algorithm or something I'm naming just randomly. And the value of X is 1, the key is equal to 1. So what happens is during encryption, H will change to I, E will change to F, L will change to M, again L changes to M, and O changes to P. So the data that is flowing on the network is I, F, M, P. So any person who's reading that data will not make any sense to that particular person unless and until he knows the algorithm and the key. So during the decryption side, what happens is the value of X is 1 and they are going to decrypt it. So during decryption, they can hop back 1 character. So again, I becomes HELLO. Hello. So the server can use this message as it is. So this was a very basic example. Similarly, you can have other algorithms as well, wherein you take the index position of HE and pass that number. So such kind of algorithms, and then the server and the client can communicate with each other on a secure network. Now, the problem with this particular symmetric encryption is, first is you have to maintain the confidentiality of the key. So the key, if it is distributed on the internet, your whole communication is exposed to the people at large. Second is your key transfer is very much essential on a secure tunnel. It should happen. So let's say the client and the server, they should ensure that the same key exists with them and that this key should not exist with anyone else, right? So there has to be a secure channel on which this particular key should be transmitted. So key management is a little bit tough. Now, what are the upsides for these systems? So upside is basically your encryption and decryptions are very fast, and it's very fast and it uses a comparatively less compute. Power consumption is right, as well as the compute consumption is less. So the use case is basically when you're uploading a file or when you're downloading big files, big chunks of data, or even on TLS, symmetric encryptions are used. We'll go in detail how TLS works and where is it used exactly, but that's how a symmetric encryption works. Now let us see what is asymmetric encryption. So asymmetric encryption is very important, a little bit complex, so we would go slow and we'll go in detail. So asymmetric encryption always uses a pair of public key and a private key, right? So every computer on the internet that is using asymmetric encryption will have their own pair of public key and private key, right? Every computer will have their own pair of public key and private key. Now the expectation is the private key should be unique to that computer and it should be confidential to that computer, right? So this private key should not be known to any other computer on the internet, and it should be only lying with that particular computer of which it is part of. Whereas public keys are meant to be distributed. So public key of client 1 can be known to client 2, can be known to server, this server, right? Whereas private key should be only known to that computer in the whole of internet, right? Now let's see how these public keys and private keys are used. Any message that is encrypted using a public key can only be decrypted using the corresponding private key. It has to be always the corresponding private key that has to decrypt that message. No other private keys can be used to decrypt that message. Similarly, any message encrypted using private key can only be decrypted by the corresponding public key, right? So any message encrypted with public key can be decrypted by the corresponding private key, and any message encrypted with private key can be decrypted only by the corresponding public key. Now let us see how we use these 2 points for these 2 points to note. It's very important. Now, let's say when your server wants to send any message to the client, right? Let's say the server wants to send a message to the client. So what the server will do, it will encrypt the message, right, using the public key of the corresponding client, or public key of C1. So the expectation is public key can be known to the other computers. So the server will have the public key of client 1, and it will use that public key to encrypt the message. Now this encrypted message would be sent to the client 1, right? And since client 1 is having the private key, and only client 1 is having the private key, it is the only computer on the internet that can decrypt this message. So even if somebody is snooping or somebody is tapping the bytes and he gets to know about the encrypted message, he will not be able to decrypt it because he does not possess the private key of client 1, right? So this point is very important, and thus we establish the confidentiality of the data using asymmetric encryption. Now let's cover the second point. So let's have a use case wherein your server, there is a client and there is a server, and the client wants to authenticate that server that please establish your identity. I want to establish your identity that it is indeed you are who you are saying you are, right? So what happens is the server says, okay, I will identify myself. So what it does is it sends a message and an encrypted message using server's own private key, right? Both the things are sent. The message is sent and the encrypted message is sent to the client. Now the client is having the possession of the public key of the server. So what it will do, it will take the message as well as the encrypted message. Using the encrypted message, it will decrypt the message, right? It will first decrypt the message, so we'll get message. Why? How will it be able to decrypt the message? Since it has the public key and a private key has been used to encrypt the message, so the message would be decrypted, and then it will try to compare the both messages. Since both messages would be equal, the client will know that okay, the person who's sending, or the server who's sending me this message, is actually having the possession of the private key for this particular server, because I am having the public key. So he is having the private key, and actually it is indeed he is who is saying. Now let's say if some person in between tampers with the message or the encrypted message, so as a result, that public key of this particular server that I have will not be decrypting this message, or will be decrypting this message incorrectly, or this message itself, let's say it has been tampered with. So this will not compare, and the client will say that okay, either the message has been tampered or it is not who you are saying, right? So the authenticity as well as the integrity of the data is confirmed, right? And these 2 points are very important. So the first point is any message that has been encrypted with a public key can be decrypted by the corresponding private key. So the public key I have for all the systems. So if I want to send any data to particular system, I will use its public key to encrypt the data, and that data is bound to only reach that particular system, or only that particular system can access that data. And if I want to establish my identity, I can use my private key to encrypt the data, and the other person can use the public key to decrypt the data and say that okay, it is you who you are saying, right? So these 2 points are very important. In TLS connections, we'll see how this asymmetric encryption works. Now let's see what are digital signatures. So digital signatures are nothing but messages which are encrypted using the private key. So let's say there's a server and it wants to create its digital signature. So it will use a message, and basically it will try to encrypt that message using the private key, and it will create a digital signature. Now why are these called digital signatures? Because these digital signatures can be used to verify the authenticity of the server. So it is server is he who is claiming to be. So we saw in the last slide, right, how we can authenticate the systems, right? So the message that is created using the private key is basically the digital signature. So that we have already seen. Now let's come to see who is a CA and who is a self-signed CA. So before we jump onto the CA, let's understand a problem, right? So let's say this client wants to authenticate the server, that it is actually the server who he is claiming to be. So let's say this this client is asking the server to authenticate. So the server indeed sends back a request, right? And this request is nothing but a digital signature, a message privately using the private key. It has been signed. Now to verify that the server is correct, it has to have the public key of the server, right? Server's public key. Now think of a system, right? Like your computer, my computer, or any other computer on the internet. If they have to connect to a network, or if they have to connect to a server, they need to have the public key of that server to authenticate that server. Now, is it possible for the client or any client to have the public key of all the servers in the world or all the computers in the world? No, right? So we cannot have, any client cannot have the public key of all the servers. So let's say if he has the public key of this server, so there can be one more server, right? Let's say tomorrow we are connecting to gmail.com. So, and day after tomorrow we are connecting to some more other servers, facebook.com, whatsapp.com. So any server that it connects to, it need to have the public key of that particular server to authenticate that server. That practically is not correct. So this particular client cannot have billions and billions of certificates within itself, right? So to counter to this particular problem, we have a certificate authority. So now comes an interesting point. How does a certificate authority work? So what happens is, this particular server, right, when he's going to come alive to the public, when he's going to expose itself to a public, so what it will do is, it will go to a CA. It will say, here is my public key. So it will generate its public key and private key, and it will give the public key to a certificate authority, right? And there are like very big certificate authorities. Google has its own certificate authority. So it will give its public key to the certificate authority, and it will ask the certificate authority to digitally sign its public key, right? Now what does that mean? So the certificate authority, it will say, okay, it's a CSR request, so basically certificate signing request. So what it will do, certificate authority will do, it will say, okay, give me your public key. It takes the public key, it encrypts the public key using the private key of the certificate authority. The certificate authority also will be having a public key and a private key, right? So what it does is, it uses its private key to sign the public key of the server, right? Of the server. Now what happens is, this becomes the digital signature, right? This becomes the digital signature, and it is returned back. This digital signature is returned back to the server, right? Now let's say tomorrow a client comes, right, and it tries to asks the server to authenticate itself. So the server, instead of sending some message signed by its private key, it will send this particular digital signature, which contains its public key signed by a private key of the certificate authority. Just hear this again. So what will happen is, this digital signature, right, it will come here, and this client is supposed to have the public key of the certificate authority. I'll tell you how. Let's say it has the public key of the certificate authority. So using the public key, right, it will try to authenticate that was it really signed by the certificate authority. Yes. So now once it verifies that, okay, your public key was actually signed by the certificate authority, so I will trust you. I will trust that you are who you are saying you are, right? So it will send its private key as well as the digital signature, and using so it will decrypt the private public, it will send the public key as well as the digital signature, and using the digital signature it will and using the certificate authority's public key, it will decrypt the public key. It will try to match the same thing that we did in the previous slide, and it will say that, okay, since it matches, your public keys also I have now, so now I don't need to keep. So now this particular client does not need to keep the public key of the server, because when the server sends the digital signature, plus the public key of the server. Once the authenticity of the system is identified, and two, the integrity of the public key is also maintained, right? Because if somebody tries to change this public key, it will not match. If somebody tries to change this signature, it will not match. The public key will not match in either cases. So the identity of the system is done using the certificate authority, as well as the integrity of the public key is also done. So the client need not have the server's public key now. Then what is expected out of client? So the client should be aware of the certificate authority public key. Now, since there are limited number of certificate authorities in the world, whenever a browser is shipped, then you need to have the certificate authorities public keys. So these are like some certificate authorities as public key that comes pre-installed on the browsers. So you need not worry about them. Those are internally stored within the browser, and those will be used to authenticate the client. So now let us see who are self-signed certificate authority. So when you're working in an organization, there are thousands of servers that are running, the test servers, the production servers, and not all of them require the publicly signed certificate authorities signature. So let's say if your clients are internal, or let's say if you're working in a test environment where a connection has to be made, a TLS connection has to be made between a client and a server. You cannot have every server going to the certificate authority and getting its public certificate signed. So in such cases, what do we do? So because why we can't have that kind of a setup is because public certificate authority comes at a cost, and to cater to such request, what happens is in the organizations, they create their own certificate authorities, and these are like internal certificate authorities. And when in such an organization, when your browsers are shipped, or when you're using a VDI or a local desktop, the browsers that are installed, they are having the certificate authority of that organization already installed on the browsers. And in such cases, the servers, they can directly go and get their certificates signed through the local certificate signing authority, and they can validate and create a TLS connection. And these local certificate signing authorities within the organization, which caters to the organizational needs, are called self-signed certificate authority. So now that we have all the understandings in place, let us see how an actual TLS connection is made. So let's say I have a client, or let's say I have my browser, right? Have my browser, and let's say my browser, in my browser I want to connect to gmail.com. So what happens is the browser, that is the client, actually makes a request to the server, that is gmail.com, and it tries to establish a connection. Now what Gmail does is it sends, so we have a certificate authority. So since it's a Gmail, I think it will use Google certificate authority. So Gmail will send me back, right? Gmail will send me back the digitally signed public key, right? And who will sign this public key? This public key will be signed by the certificate authority, which in this case is Google, right? So a public key of Gmail would be sent to the browser back, and this would be digitally signed. Now my browser is shipped with the certificate authorities public key. So what my browser does is it authenticates, since it is digitally signed by Google certificate authority, that is the private key of the Google would have been used to sign this particular public key. So this digitally signed public key would be decrypted, and the authenticity of the server, that is gmail.com in this case, would be established, as well as the integrity of the public key is ensured. Now my browser has the public key of the gmail.com, and it knows that on this TCP connection I am actually talking to gmail.com. So what it does is it creates a random key. This is important. Now what it does is, once it knows that the authenticity as well as the integrity of the public key has been done, it creates a random key, and it encrypts it using the public key of the Gmail, which it got in the second leg, right? Using the public key that it got, it encrypts a random key. It generates a random key and then it encrypts it. And then this encrypted data is sent to gmail.com. Now this encrypted data is then decrypted using the private key, because Gmail is the only one who's having its own private key, right? So since this was used encrypted using public key of the Gmail, the encrypted data, from the encrypted data, Gmail will get the random key. Now in the whole of universe, these two computers are the only computers that are having these random key. This computer, that is my computer browser, is having it because I generated it, and the other person is having it, that is the server is having it because it used its private key to get the message back. Now what the system will do is, all the connections, now a TLS connection has been made and the two systems here are having a randomly generated key, and it is ensured that only these two computers have access to this random key in the whole of universe. Now what will happen is, all the further communications, whether it is from the server to the server, to the client, from the client, will be used using symmetric encryption. So till now, while establishing a connection, TLS connection, we used asymmetric encryption. And once the keys have been exchanged, random keys have been exchanged, now all the communications happen on the symmetric encryption, because the basic idea of symmetric encryption is you have a single key that is shared by both and is unique and it is isolated from the whole world, and two systems should only be knowing these key. So now all my future request becomes very fast, as well as secure, as well as compute is less, since it's a symmetric encryption. So this is how a TLS connection is made using an asymmetric encryption, as well as and further the TLS is maintained using symmetric encryptions, and this TLS encryptions is made on a single TCP connection in a HTTP protocol. That's why we call this HTTPS, because it's a secure layer that has been added. Security has been added. Any person who is accessing any of these data throughout any leg will not be able to make any sense, because these are all encrypted data and nothing can be decrypted from by the person P who's snooping on the data. So now let's see how man in the middle attack is avoided. And we've already seen this, how we stopped snooping through TLS multiple times. But let's see this in action. The client, let's say, someday tries to make a connection to the server, and it requests for a TLS connection. So the server, let's say it has already validated its public key and got the digital signature. So now the server has the digital signature as well as the public key. So it returns back the digital signature as well as the public key, and the client makes a successful connection with the server. Now this connection is made. Now tomorrow, let's say the client again comes to the server to make a TLS connection, and this time a hacker has hacked some DNS router in the system, and all the connections are now routing to this particular server. Let's say that has happened, and the hacker has the public key. How has he got the public key for the server? This particular public key, let's say it has with it. How? Let's say someday tried to make a connection, and due to which the server gave its public key and digital signature to the hacker. Now this hacker, let's say it is routing this particular public key as well as the digital signature as it is to the client. So the client, what it does is it creates a random key, uses the public key of the server, and it routes back the request. Now this hacker, although it knows the public key as well as the digital signature, it does not have the private key. Private key still lies with this guy, that is the actual server, and so it will not be able to ever decrypt this message, and so there will be no TLS connection that will be made, and the TLS connection request will be failed. Now let's say what it does is it changes the public key so that the client uses a different public key. But as soon as he changes the public key, the digital signature no longer matches the public key or verifies this public key, right? Because the digital signature was made using the private key of the certificate authority with the public key of the server. So again, the hacker would fail, and the man in the middle attack would be avoided. Now let's say someday what happens is, this hacker someday creates its own public key and private key. It creates its own public key, private key, and gets its public key digitally signed by the certificate authority. And now it sends its public key and digital signature to the client. Now what happens is, actually in real systems, when a certificate authority is signing a request, right, it does not sign only the public key, right? The whole certificate is signed, and that contains the domain name, that contains multiple other details, not only the public key. So this certificate, when it is digitally signed, it creates a, so first this certificate is used to create a hash, right? Let's say a SHA-256 is used. Now the beauty of the hash is you cannot get the message back from the hash. So hash is created. This hash is basically signed. Now what happens is, first the certificate authority will never sign this guy's certificate because the domain names are different. It is trying to imitate somebody else. Certificate authority already knows that I have someone called gmail.com that I have signed, so I cannot sign another gmail.com, right? And the other thing I see is the SHA that gets generated, right? So tomorrow, let's say if this hacker gets the certificate, direct certificate, it gets the digital signature, it gets the public key of the server. Using the digital signature, it gets the certificate, right? And using the certificate, it goes and modifies the public key in the certificate. As soon as it modifies the public key, the SHA changes, right? So what happens is, in the certificate you have public key, you have domain name and many other details. As soon as you change any of the fields, now the hash changes. Since the hash changes, this hash and the publicly signed hash is no longer the hash signed by the certificate authority is no longer the same. So this hacker can now again fails in the attack. So this is how TLS stops any man in the middle attack, and if implemented properly using proper checks and balances in place, this can really avoid these type of attacks in future. So let us now try to see the certificate in action. So I have opened google.com for you, and we will see that the connection is secure. It's an HTTPS connection. And we also see that if you click on secure connection, your certificate is valid. And if you go to details, you will have a lot more of details. So if you see, this is the certificate that I'm talking about. You can export it in the PEM format, or if you expand the certificate, this is the different fields that the certificate has. So when the client gets this certificate, right, the very first thing it does is it goes and checks what is the signature through which the hash was created. So we see that it's SHA-256. So what it will do is, like, it will first try to create the hash of the certificate using the fields. Now once the hash is created, what it will do is it will go and see the signature value. Now it has the public key of the certificate signing authority. So using the public key, it will decrypt this message, and then it will try to compare the SHAs. If both SHAs are same, that means that this certificate has not been tampered with. Now once it ensures that the certificate has not been tampered with, okay, and so it ensures that it is actually the person who he's saying who he is, and then it takes the public key. And using this public key, if you see, right, certificate, and public key, then it goes and checks what is the algorithm that this particular certificate is using in case of asymmetric encryption. So if you see, right, it will be somewhere here. So yeah, so subject's public key algorithm. So the subject's public key algorithm is elliptical curve public key, which is basically a asymmetric encryption. It can be RSA, it can be elliptic curve, and in case of symmetric encryptions, it can be AES encryption or DS encryption, and it will basically send the public key to the client. This public key comes to the client, and then using this public key, the client sends a random key, and then random key is again decrypted at the server end, and then these are the two systems in the whole world that is having this random key, and then the symmetric encryption starts for the rest of the data. So this is how the certificate looks like. You can export so these certificate values, if you see, these values will not make much sense to you, as these are all base 64 encoded. And if you try to export this, it will say you can export this in the PEM format. These are the public key certificates for that particular server, right? One more thing I wanted to cover at last is mTLS. So we saw that what is TLS. Now let's see what is mTLS. M stands here for mutual TLS. So till now what we have done is we have authenticated the servers only, but that's not the case always. Sometimes you need to authenticate the clients also. So the servers can only connect to the specific clients. Now think of a system, a closed system, where one of the services is talking to the other service. So sometimes these other services to whom the clients are talking, they do not allow connections from anyone and everyone. They only can allow connections, let's say, from a few of the services, and the rest of the services they don't allow the connections. So they can basically whitelist these particular clients. And in a similar fashion, how we have seen the servers authenticating themselves, the clients also establish their authenticity, that it is indeed they are who they are. And then once that is done, the servers, then once they know that this is actually the client that wants to talk to me and he's not fake, and also he ensures that this client is actually allowed to talk, then they can establish a TLS connection. So that is basically the server as well as the client both establishing and authenticating themselves and establishing the TLS connection, and that is why it's called mutual TLS. So that was it, guys, for today. If you like the video and learn from it, do consider liking the video. And you have any specific topic or any suggestions, do let me know through comments. Thank you.